请挤出话筒。
Hello, hello, testing. Okay, good morning to everyone. Seems like not many people are here. Do you have assignment due or CP? Do you have assignment due like other course, or do you have test quiz, something like that? No. Okay. Sleeping. Half of the class sleeping. Okay. Let's start. Let's not wait. Okay, let's continue with our curve sketching. So how do we sketch the curve? So there are basically 1, 2, 3, 4, 5, 6, 7, 8, about at stake here. So actually, if you notice, step A to step D is covered in chapter 1, and then step E to G is covered in chapter 2. Actually, curve sketching we already learned in chapter 1, but those are just for the simple basic curve. For example, polynomials, trigonometry, rational function, and so on. But the step that lay out here, right, can help you sketch general curve. Okay, help you to sketch the general curve here. So first step is to determine what points that f is defined. So this is called the domain. And then step B is to see when you intersect the x-axis and y-axis. And step C is to see whether this function have any pattern. So meaning, is it even? Is it symmetric across the y-axis? Or is symmetric around the origin when it is not? Or it is periodic, okay, meaning it repeats the pattern for a fixed interval. And then D is to find horizontal asymptote and vertical asymptote. Okay, where this function goes infinity or it approaches some horizontal line. And then E, okay, E is to determine when the first derivative greater than 0 or less than 0, meaning when the function going up or decreasing going down. F is to see whether there's any local maximum or minimum. So meaning you have peaks or not. Okay, you have crest or not. Okay, these are to use the first derivative test, or you can use second derivative test also. But since we're already searching for first derivative E, maybe first derivative is better to use so that not to involve too many calculation. G is to check the concativity, okay, whether it's concave upward or concave downward. Okay, still remember what is concave upward and downward? It's Felicia, right? Do you still remember what's concave upward and downward? And second derivative is positive, then it concaves up. And then less than 0 is concave down. Okay, let's check. Hey, let's check, is it true or not? Where's the concave up down lecture? Okay, so this concavity theorem here, if your second derivative is positive, it's concave up. If it's less than 0, it's concave down. Good. Okay, very good. But what's concave up or concave down? Definition. How the shape looks like. Going up. If going down, can it be concave up? It could be, right? Uh, so concave outward just means that your graph will live above the tangent line. Okay. So you can decreasing but concave outward. Okay, you can increasing and concave outward. Similarly, you can decreasing when you concave downward, or you can increasing when you concave upward. But this is about tangent line and the curve, the relation between tangent line and the curve. So if you notice that for concave upward, concave downward, right? How can they increase? Okay, can you see the different way they increase? Okay, if you put these two together, it forms like a eyes, right? Okay, so these are the two way to increase. Okay, does it make sense? Okay, so one way is concave upward, one way is concave downward, depend on whether your curve live above your tangent line or below your tangent line. Okay, both of them can be increasing or decreasing. So please take note. Okay, the thing is whether your curve lie above the tangent line or not. If you are Chinese, right, I think this measures up our Chinese character, right? So concave downward, you can think of this two, right? Correct? So two is like a bit discrete, so we join it, become continuous. And then here is like how you can write here. Right? Make sense? Okay. Do you call concave outward out? Is it out in Chinese? Is it called out? Concave outward. What's your term? For the Chinese student? What's the term for concave outward? Not sure. Out, huh? 对吗? Out, right? 上凹. Okay. Yeah. Because it is really out. Okay. Okay. Yeah, Chinese character is like how to say? Mm, it's about shape. Yeah. So Chinese character grow out of shape. For example, water. What else grow out from shape? Like river. These words are growing out from shape. Chuang, right? River chuang. So it's like maybe let's draw a bit. A Chinese character for river is like chuan, right? So you can think of like the river flowing. So Chinese character is really a geometry actually. Geometry. Okay. So let's continue with our examples. So last time we were asked to sketch this graph here, 2x squared over x squared minus 1. And we determined that the only place this f is not defined is minus 1 and 1, because if you evaluate this function at this point, you get 0 in the denominator. But something over 0 is not defined. Okay, so this point are the point where this function is not defined. And then step B, we're going to find when it intersects the y-axis. So meaning when x equals 0, or we want to find when this function intersects y-axis. This is when s equals 0, intersecting x-axis, it is when y equals 0. Okay. Okay, but in this case here, we found out that there's only really one place in axis and y-axis, which is the origin. And next, we check what is f minus x. We want to compare it back to fx. Okay, in this case here, it is even. And if it is even, it is not odd anymore unless it is a zero function. It is not periodic because you cannot just add a finite value to your x such that you get back the same value. To show this rigorously, maybe take some work, but I think you can try and substitute and then see that you get a bizarre expression that you can't get back your original expression, meaning you cannot remove this p. And then D, you gotta try and find a horizontal and vertical asymptote. And then last Wednesday, we determined that there are one horizontal asymptote and two vertical asymptote. Okay. Based on where they should go to infinity, we guess the shape is like that. Okay, so we guess this is the shape. Okay, so if we want to continue with the step, right? So for example, we want to find where increasing or decreasing. Based on this shape, can you see that where increasing, where decreasing? Okay, so everything on the left axis, left x-axis from a zero, from the origin, it should be increasing, right? Everything on the right of the y-axis should be decreasing. Okay, we should expect this calculation. And then if this shape is correct, what's the next thing we need to check? Where's the local maximum or local minimum? If this shape is correct, just the origin is a local maximum. There's no local minimum here. Everything is going down or either going up. And then G concavity, if this shape is correct, so where is concave upward or downward here? So basically you can split this picture into three parts, right? So the left, middle, and the right part based on the vertical asymptote. So on the left one, it should be concave upward because the curve is above the tangent line. And then in the middle one, the curve is below the tangent line, so it concave downward. And then on the right, again, the curve is above the tangent line, so it's concave. Okay, so we could guess what we should compute here. There's no inflection point because there's no point such that on the right hand side is concave up and the other side is concave down and vice versa. Okay. Does it make sense? Okay. So let's try a calculation now. Yeah, let's try it. So we start with step E, right? Let's continue with E. Maybe you can compute together with me so that you are not that boring. See if you get the same answer as me or not. Okay, so to find interval increasing or decreasing, so let's find what is f prime x. Okay, so here should be clear that we are using quotient rule here. Yes, so if we use quotient rule, please check my answer. We get this minus 4x over s squared minus 1 squared. So let's check when is it positive. Okay. So note that the denominator here is always positive. So it won't change if any sign change happens. So the only possible sign change happen is negative 4x. Okay. So negative 4x will be positive if x is negative. and f prime x is less than 0 if x is positive. Okay, so hence f is increasing on the left hand side of the y-axis and is decreasing on the right hand side of the y-axis. Okay, so this matches out what we predicted just now. All right, so you can see that here only cover f prime x greater than 0 and less than 0, right? So how about equal 0? So equal 0 is exactly the next step, okay, where the critical point happen, or more specifically, the stationary point happens. Not that f prime x equals 0. When is it? It is when x equals 0. Okay. So to make this 0, you make your numerator 0. But the way to make your numerator 0 is x equals 0. You can sub 0 into your f prime x. For minus 4 times 0 over 0 minus 1 squared. So 0 over 1. Okay, so from E, we see that this value here is a local maximum value. Okay, so why? So let's recall the first derivative test. So what does the first derivative test does? So maybe you can draw a x-axis here. Okay, draw your local maximum point here, which is 0. Okay, so just now we just determined that on the right hand side, sorry, on the right hand side of the 0, we should get decreasing, which is negative, negative first derivative. Okay, so it's decreasing. And on the left hand side of 0 is positive derivative, so which is increasing. So you increase and then decrease. So meaning this point is a local maximum. Okay. If it is decrease and then increase, it will be a local minimum. Okay, make sense? Okay. So we got our origin as our local maximum. So if you, yeah, okay, let's continue. So G, okay, G is what? G is concativity. Okay, so we need to differentiate again. Okay, differentiate the second time. So let's continue differentiate. So if you differentiate the next time, okay, let's write down the first step and then I will show you the final answer. You can try and compute yourself also and then check with the solution. So you do some simplification, and we'll get this nice and clean expression here. Okay. So if you look at this final expression here, right, the numerator contains what? Positive number only. Okay, x squared is positive and then 3, 1, 4 are all positive. So this means the numerator here now become always positive. Okay, so the problem here is the bottom here, x squared minus 1. And so if x squared minus 1 become negative, then cube of a negative number will be negative. So let's check. So you can see that it's really the similar analysis we do on first derivative and second derivative, but this value will mean different things. Okay, this value will mean different things because the first derivative is about the changing of your graph, but the second derivative is the changing of your tangent line. Okay, so this is the different interpretation we put on the same analysis. Okay, so same analysis, we should check where is it positive, where is negative. So if f prime prime double prime f of x is greater than 0, then we have to make sure that x squared minus 1 is greater than 0. Okay, because numerator is already always positive. And this will implies that x squared is greater than 1, but this just means that x has to be greater than 1 or x has to be less than x. And on the other hand, if you want to make sure that this portion here less than 0, we need to measure that x squared minus 1 is less than 0. Okay, which means that x is in between minus 1 and. Is everyone okay with this inequality for quadratic? Okay, everyone? Or you need more detailed step? Or do you know any method to see? Okay, so basically, uh, maybe I can talk a little bit more. So basically, if you want to look at this inequality, right? On the right, on the left-hand side here is actually a function. Okay, so you're asking when this function has value greater than 1. This is what you want to ask. But this function, you know how to draw, right? I mean, this is x squared, right? Okay, so you ask yourself, when is it greater than 1? What's the value that are great? What's the x value such that it's greater than 1? Okay, but maybe it's more convenient to look at the first one here. Okay, if you look at the first one here, do you know how to draw the left-hand graph? So it has root at -1 and 1. And then you ask, when what x you take, you have a positive s squared minus 1 value. Okay, so these are those away from less than -1 or greater than. Okay, make sense? Okay, so hence, like what Felicia said just now, based on this, we know that f is actually concave upward on -1 minus infinity to -1 and 1 to infinity. Okay, there are two sides. And also, it is concave downward on, where is it concave downward here? On -1 to. So this is exactly the shape we draw just now. Yeah, so I use GeoGebra to do it. So this is exactly the shape we predicted. Sometimes the horizontal or vertical asymptote is enough for you to give the whole shape, where the rest is to check. Any questions so far? No? Okay. I think there are a few more examples which you can try out yourself. For example, x squared over square root x plus 1. Okay, so you do all the similar steps and then you get some shape like this. It's not too far right from the original, on the, I mean, more accurate graph here. So basically, in this example, I just found one vertical asymptote. And then, so based on this graph, right, can you describe it? Where is it increasing or decreasing? Where is this graph increasing or decreasing? Yeah. Okay, try. Where is it increasing or decreasing? Yeah, good. It's increasing. Okay, good. Yeah. And then there's only one vertical axis top. And then where is it concave upward or downward?
When x is positive, is up,
Okay.
and when x is negative,
Upward or downward? Also upward, right? Yeah. So this is your tangent line. Okay. Yeah. So this is the calculation. You see, x greater than -1 is concave upward. Okay. If it concaves downward on the other side, your graph should look like this. Okay or not? If this is concave downward. Okay. If concave downward on both sides, then you get something like this. Yeah. Does it make sense? Okay. So different way of increasing and decreasing. Or if on the other hand, you want another combination, maybe you concave upward decreasing, and then you concave downward increasing like that. Okay. And okay. Yeah, but in this case here is concave upward always. So this graph I graph out is not too far from the original graph. Original graph is more steeper, so meaning it increased even faster. Increase even faster. Next one I think is also similar, but I recommend you try this one. This the last one here. This last one here is very interesting. If you haven't finished all the steps, you wouldn't know what's the shape. Whereas this one is very interesting. This is not some basic shape you have seen before, and it is a periodic. Yeah, it is periodic, and then surprisingly, this period uh, is not too hard to see actually because cos and sine are periodic. Okay, and then this shape is something like this. When you find a local maximum, a local minimum here, maybe it's a bit weird when you first look at it. You can try this example. Okay. Okay. Any questions so far or whatever we learned up to now before we go to application question? Any question about finding asymptote limits and local maximum minimum activity? First derivative test, second derivative test. I think we decided not to give you this kind of long question, but maybe we'll split it up to different questions. Okay, so you won't like die in one long question. Right? So you could have different function to compute. But make sure that you can graph the basic graph. Still remember the quiz one, you have a basic graph and then we stretch it. We can translate the graph. How to construct new graph from old graph. Right. So that chapter is very important. But this kind of curve sketching, right, will help you to draw a more complicated curve. So you can actually, without using software or computer, you can actually guess the shape already. Okay. Any question? Any questions so far? No. Okay. If no question, then we'll go to application question. It's my Okay, so let's continue with optimization problems here. So meaning we want to find the maximum or minimum of some quantity. So this will be related to the local maximum or local minimum. Okay? Finding the first derivative, finding the stationary points and so on. Singular point. So critical points consist of boundary point, singular point, and boundary point, singular point, and stationary point. Okay, so these are the 3 points you need to check. 3 type of points. Okay, so let's look at this examples here. So a rectangular box is made from a piece of cardboard, 24 cm long and 9 cm wide, by cutting identical square from the 4 corners and turning up the side. So find the dimension of the box of maximum volume. What is the maximum volume? So since it is a rectangular box cut out by cardboard, so cardboard should be rectangular as well. So let's draw it first. So it's 24 cm long and 9 cm wide like that. Cutting out identical square from the 4 corners. So what does it mean? Any idea? What does this mean? Hmm. Hmm. Ah, good, good. Okay, so you put 4 square from the corner at the corner, yeah, and then cut it out. Very good, good. Good picture. So for square here, okay, square on the other side. And put one more here. And then you put one on the other side. And you cut out 4. So these are identical square, right? And that square have same side on same side, same length of side. Okay, so let's label it x. Okay. And turning up the side. So can you imagine that if I cut out the square, right, then you just flip the remaining side up, then you can form a box. Well, this box is not covered. Okay, it's opened. Okay, so I want to find the dimension of the box of maximum volume. Okay, so if you imagine you cut out the corners already, right? And then you flip out the side. What's the volume? What's the formula of the volume? What do you think? What's the height? What's the length? What's the width? Maybe tell me what's the height first. What's the height of this box? What do you think? X, right? Okay, because this is how long you cut it up, right? How long you can flip it up. Okay, so this is X. Then how about your length now? What's this length here? 24 minus 2x. Okay, so 24 minus 2x. And your width, similarly, it is subtracted by 2x as well. Too long already I draw, I think just here. Okay. So the question asks about maximum value, meaning when this volume will reach the maximum. Okay, when will it reach the maximum here? So maybe I'll ask you a question. Is this function here always positive? Is this function always positive? How do you know? How do you know? Is this always positive? Huh? Ah. Or maybe you just substitute some value and then you see that some value will give you negative number, right? Okay, yeah, good, very good. Okay, so you can use substitution or you can just graph it up. Okay, maybe you will go to negative part of the y-axis. Okay, so if you expand this, I think what you get is 2 times 108 x minus 33 x squared is 2x cubed. Okay, so you need to be careful, okay, for the local maximum or minimum that you find. Make sure that that value really give you some meaningful number here. Okay, you don't want to pick the negative one. Okay, you want to pick the positive one. Okay, so what is dv dx here? So this is just polynomial, right? Should be easy to differentiate. Please check my answer. Okay, so we want to find maximum here. Well, there are critical point to check. Maybe 3 types actually. Okay, so what are the types? So first type is the boundary points or endpoints. Second is the singular point. And lastly is the stationary point. 驻点, right? Stationary point. Okay, so any boundary points here or not? There's no boundary points here. Why? Because your function is defined everywhere. Okay, so there's no finite interval defined, so you don't need to worry about boundary point. So this is about checking the this is about checking the absolute maximum. Okay, so this is about checking absolute maximum. So local maximum, you just need to check for your first derivative is you just need to check about your first derivative, the first derivative test that we do just now. But now you want to find for maximum value volume, right? I think they should ask you for the absolute maximum. Okay? The largest one, the largest of the largest. Correct now. Maximum above all value. Singular points, do you need to worry about? So here, no boundary point because the domain of F is everything, okay? Not a finite interval. Singular point, okay? No need to check also because every point is differentiable. Okay? There's no point that is not differentiable. Polynomial is nice. So now we just left with stationary. Okay? So these are the point where the tangent lines stay static, horizontal. Okay, so these are the points you need to check. Okay, so if dv dx equals 0, okay, this means that our quadratic function here has to be 0. So if you do factorization, you will get x minus 9, x minus 2, which implies that our stationary points are 9 and 2. Can both of this be maximum or not? Or minimum? Can. Can both of them be maximum? Cannot? You sure? It could be, right? If they take the same value. Right? If they take the same value, it could be. But I think if some of you know that this function is injective, then you know that these two must certainly take different value. Right. So what should we do next? Depend on how you want to proceed. You want to use first derivative test, you can, but I choose to do second derivative. Okay. If you want to do first derivative, you can, but I do second derivative test. Okay, so if I continue to differentiate, I get even easier function here. Okay, so to use second derivative test, what do? We just evaluate as well. Okay, so when x equals to 9, I get dv square, d square v dx square to be 84, which is square root 0. And then when x is equal to 2, we get blah 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 equals to negative 2. Okay, so by second derivative test, v9 is a local minimum because the second derivative square is 0, and v2 is a local maximum. So there's no boundary case to worry about. So this local maximum should be the maximum we want. Maybe you should compare to be safe, or maybe to be safe, just compare. So what is v2 here? Not that. v2 is equals to the substitution that you have to do. So 2 times 108 times 2 minus 24 times 2 square minus 9 times 2 square plus 3. Okay, so this is 200. 200. I think it's 200. Yeah, I think it should be 200. But I haven't computed what is V9. Anyone can compute what is V9 here? Should be greater than this number. What is V9? I suspect it's negative. Negative. So what is it? What's the negative value? Maybe you can press your calculator. What's V9? Anyone try? What's V9? What's V9? Huh? Why not? Press your calculator. Not right. You can press your computer. What's V9? Anyone got V9? What do you get? What do you get? Minus 486. Minus 486. Okay. Okay, so the dimension of the box of maximum value is 24 minus 2 times 4, 2 times 2 times 9 minus 2 times 2 times 2. So which is 20 times 5 times 2. Okay, so which is about 200 cm cube. So I give out the dimension, I give out the volume. If you want, you should write down the unit as well. So they are in cm in the question. Okay, so you need to be careful when you compare about this local minimum and local maximum here, right? So it could be the case that a local minimum is higher than a local maximum. Can you imagine? Can you imagine a case that local minimum is higher than a local maximum? Can you imagine what the graph should look like? So local minimum is like this, right? Local maximum is like that, right? Then maybe it could be the case that something happens like this. Right, then this local minimum here will be greater than the local maximum. Okay, but if it happens, then if your graph is continuous, then you should have more local max or local min. You should have more. Okay. So so the point here is don't just see minimum must be the lowest. It's not the case, right? Because this is just locally true. It could be the local minimum here greater than a local max. Okay, makes sense? Okay, so you need to be careful when you try to find maximum or minimum. And then try to determine whether the people that ask you want the absolute maximum or local maximum. Okay, do they want the really big one or they just want within some region it is the maximum? Okay, you need to ask yourself. Okay, next 4.5.2, 4.52. Okay, let's do this one and then we will break for 10 minutes. Okay, so a farmer has 100 meters of wire fence, with which he plans to build two identical adjacent pens divided by a single layer of fencing. What are the dimensions? Okay, again, what are the dimensions of the enclosure that has maximum area? Okay, so what does it mean by adjacent pens here? So it's just where you should grow your veg. So the pens is like a rectangular shape, okay, but they build two identical adjacent pens. So meaning this rectangle should be split into two identical parts. Okay. So if they are identical, that's mean what? That's mean their length should be the same, or maybe call it YY, and their width should also be the same. So let's call it XX. Okay. And the farmer just used 100 meter to build this. Okay, so meaning what? Given XY in the picture, okay, given XY in the picture, then we know that 4x plus 2y equals to 100 meter. Or maybe we can rewrite this y equals to 50 minus 2x. Okay, so we managed to write the length in terms of the width. Yeah. Okay. So meaning what? This makes sense, right? This makes sense to real life, right? How many length you put on the width? Sorry, yeah. How many wire you put on the width should affect how long this pens could be. Because you really only have 100 meter of it. You cannot get more than it. Okay? So this is very accurately describe the real situation here. But now the question is about area. Okay, now the question is about area here. So in real life, what do you do? Maybe you build a fence and then you compute area. You build a fence, compute area. You build a span, compute area, and then you compare which one is the largest. Okay, but this is very inefficient. Okay, the more efficient way is to use derivative. Okay, so we can use derivative to do it. So let A be the area of enclosure. Okay, so area here is just which one you want to maximize. I mean, if you maximize one of them, you are maximize both of them, right? So just compute one of them is enough. So A xy equals to 2x. Okay. Or should we do both of them? Okay, to be precise, let's say area of one pence. So let's maximize once, and if you maximize once, it should be maximize both of them. Okay. So what should we do next? But notice that this area, right, we are writing it in two variables, but we only learn one variables, differentiation. So given the case, is it possible to reduce to one variable? Yes, right, because we have y in terms of x. Okay, if not, then you need to do the implicit differentiation. Okay, if not, you need to do the implicit differentiation. But luckily, we are okay. From assumption. Actually, A, we can rewrite it as just a very function of x. So 2x times 50 minus 2x, which is 100x minus 4x. Okay, again, we want to find the maximum. Okay, so you should go through the argument I showed you just now, critical points. So what do you need to check? Three type of points, right? Boundary points. Yeah. No, it's not. It's not. It's just I want to show you that across this green line here is identical. It's not. It's not. That's also the reason why I put it in a different color. It's just to show you that it's not right. Let me see. Fire fence. I don't think. Maybe you can. Wait, let me see. Okay, I feel like no. Okay, because let me argue. See whether it makes sense. So if you look at this question, right, it just says that this 100 meter is used to build two identical adjacent fence, and then divided by a single layer of fencing. I feel like this single layer is an extra fencing that you put. No, you don't think so? You don't think so? You don't think so? You want to include it in? Why? Yeah, sure. So let's decide whether should we add this extra fencing to our 100 meter. Why? Maybe you try argue. See, I convince someone. Gabriel, right? Gabriel, is it Gabriel? Gabriel, yeah, Gabriel say we have to add. So what? I also explain according to the question. Uh-huh. Uh-huh.
What is one? Yeah. One. So it's part of the what is the one? It's two planes that put together. So
Yeah.
it's only five. Instead of it being two, it's one.
Oh, okay. Okay. So Gabriel says that maybe you can start with imagine with two pens. Okay. But the question said that the bigger layer here, you just use a single layer instead of double layer. So what do you think? Okay. Should it come from the 100-meter fire pen? Maybe Jiachen, right? Jiachen also said you should add it in. Okay, why? What do you think so? Why? Who else think you need to add the single layer and sing it? Yeah, you think so? Okay, let's try again. Mhm. It's not necessary to send an extra layer of fencing. Okay, okay. I think yeah, sure, cool. I think makes sense. So let's add it in. Let's add it in. So maybe then this will make our differentiation harder, right? Yeah, never mind. So let's add it in. This become 3, right? So okay. Okay, good. So then this make this question harder already. Let's try. Let's try. Okay, so we cannot directly substitute. Can we? I think can, right? Because it's just divided by 3. It's not a square. So I think it's fine. So y is equals to 100 minus 4x per 3. Okay. Just that not as nice, but still substitutable. So then, again, by assumption, assumption. In this case here, do you want to maximize the whole, the whole enclosure, or you want to just maximize one pen? Maybe everything do it together in this case. Let's do it for xy. Is it for xy? Oh, just 2xy, sorry. 2xy is enough, right? This is so this side here is 2x, and then this side is y. Okay, if it's one pen is xy. Okay, two pens is 2xy. Okay, so then we can rewrite our a. X become 2x times 100 minus 4x over 3. Okay, which is 2 over 3x times 100. Maybe you can pull the 2 up. 50 minus 2x. Okay. Maybe this form is not nice for integrate differentiation later. So let's just multiply it out. So it becomes 200 over 3 times x minus 8 over 3x. Okay. So similarly, you check the 3 types of critical points, boundary points, singular points, stationary points. But in this case here, there's no boundary point to check because it's defined for every points in R. And a singular point, this is very well differentiated, right? I mean, differentiable. Okay, so you get derivative at every point. There's no singular point. Usually, you get singular point when your derivative is like divided by x or divided by something that can become 0. But please learn how to show something is not differentiable. I think when you learn in class. is to show by the limit definition, left and right. It's different. Limit of the secant function. Okay, so mm, right. So let's just check for. So maybe I remark here there's no boundary point or singular point to check. Let's consider a prime x equals 0. Okay, so this means that if you differentiate, you get 200 over 3 minus 8 over 3 x equals 0. Then what's this point here? So then this is x equals to 3 over 200. Sorry, 200 over 3, and then times 3 over 8. So you will get, is it divisible? Is it divisible? 2x 1650. So what's the unit you use here? Meter. Then then what's the dimension here? So the dimension, hence the dimension of the enclosure with maximum area is what? So formula with x times y, right? Okay, which is 2 times 25, 2 times 25 times y. So what's y here? So y here is yes. Sorry. Oh, 16, 16. Thank you. Why am I thinking 25? Oh, hey, wait. What's 16? 8. Ah, thank you very much. Yes, thank you very much. This is after differentiate, your power need to come down. So this is 16 here. Then this is not a whole number anymore, is it? So the up, what do you mean? Correct, okay. So 200 divided by 16, what do you get? Huh? 4, 12, 12.5. Okay, good. So in this case here is 2 times 12.5. Is it easier to work with 12.5, or let me see what's the fraction you get? What's the fraction you get? 450, 50 over, so it's 25 over 2, right? Okay. So how about your y? Maybe fraction is easier to work with. So 100 minus 4 times 25 over 2 over 3. Okay, so what do you get? 25 times 50 over 3, like that. I think this is the nicest way to put it, instead of writing unlimited decimal expansion. Okay, I think that's good. Question? Any question or not? Before I finish, take a break. Any question? No? Clear? Okay. If no question, let's break until 10:15. Oh, is it possible that some of you went to the Huawei competition? Huh? They went to Huawei competition. What's the Huawei competition? Coding. What's that? Don't know. No idea. Why some of you know about the competition, but some of you don't know where they get the leads from? Uh-huh. Announcements. Oh, I see. Is a coding competition or what? Not very sure. Okay, so 西河 got 乐天、瑞妍、瑞妍、瑞阳或瑞妍、瑞阳。若石、若石、陈若石。OK，诗曼、一南、一泽、丽文、丽妍。泽汉、嘉来、嘉诚和嘉诚。I think go toilet. 嘉诚，right?
Yeah.
嘉诚。嘉怡、吴嘉怡。OK。齐军、黄齐军、黄义清。季俊义、施阳、雷艺林、冰珍、冰珍那边。他 quiz 来得及。他昨天。嘉谈和浩云、文琪，OK，汉翔，不是汉翔，汉翔好了，刘汉翔，然后 here，刘俊杰个刘新阳，万达呢，新月、玉恒，OK，一田、冰城、苗冰城，浩然个，OK，now it's rest，that's OK。Desmond Tan, Desmond at the back. Okay. For me, what's called? Okay. Hey, Desmond got another Desmond. Oh, at the side. Okay. Chong Yi, India, India got Pagani here now. Arthur, Jose, Isham, Daniel competition. Hashim, is Hashim here? Hashim, Madia competition. Aaron got Brandon at the back, right? Brandon, Alicia got Gunakanti. Okay. Margaret got Khalid got no. Hassan Khalid. Haven't seen for a long time. Hassan Khalid. Javed got Gabriel. Jeffrey at the back. Purity here. Okay. Chen Fan. Chen. Okay. 何雅婷。Yeah. 吴以叶。Okay. 郭洪亮。Okay, please be reminded, quiz on next Monday, 3 p.m. Any problem, please message me or email me. You are. Oh, Han Xiang, yeah.
Thank you.
Okay. Okay. Hey, something I missed in this calculation. What do you think? I just checked stationary points. What do I miss? What do I miss here? I straight away deduce the maximum solution. What do I miss? What step I miss? What do I miss? If you're a lecturer, you see this in the student exam, I give full marks or not? You check stationary point and then you deduce this is a maximum. You give full marks. What do I miss? Jose, is this solution correct? Full mark? The question we did just now. What do you mean different from calculation? Which result? 0.5? You mean this one? 2. You mean the length this one? 2x times y? What's different? X is 25 or y is 25? Y is 25? You mean I compute wrong? Huh? What? It's different, but you can check calculation, right? Have you checked? So is it correct or wrong? Huh? Did you check? Sorry? And then? Yes. Okay, so either you use first derivative or second derivative to decide whether it's a local max or local min. Okay? To make sure that it is a maximum. Okay? So because there's no boundary points, right? No singularity points, right? So this local maximum, the highest one will be your absolute maximum. Okay, so make sure you use the first or second derivative here. Check whether you get a local maximum or local minimum. Because there's no boundary point or singular point, so you just need to worry about your local maximum. So what test I use here? So this question here, because the first derivative is nice to check, you can substitute, but I think second derivative is even nicer. Second derivative is just -8. It's always negative. Okay, so second derivative is even nicer. So first derivative is good, but second is nicer. So consider a prime x, which is -16/3, which is less than 0. Okay, so x is a local. So x equals to 12.5 is a local maximum point. Okay, so x is a local maximum point. X equals to 12.5 is a local maximum point. Fx is a local maximum value. Okay, in terms of m or not cm here, sorry, it's meter. Okay. All right. So, okay, maybe let me ask you, since we know that this is a local maximum point, right? If you use first derivative, what do you expect? On the left-hand side, is a positive or negative? Huh? If you use first derivative test, what do you expect? On the left-hand side should be positive, right-hand side should be negative. Okay, so if you substitute values into your first derivative here, okay, if you see something less than 12.5 here, you should get positive. Greater than it should get negative. Okay. So here a prime x is greater than 0, on the other side less than 0. Okay. Next, should we do this? This question is a bit tricky. It uses a similar triangle that we have met last time. If you still remember the arrow plane question, okay, let's see what it asks for. Find the dimension of the right circular cylinder of greatest volume that can be inscribed in a given right circular cone. Okay, so meaning you want to put a circular cylinder inside a circular cone, and it is a right circular cone. So let's draw the cone. Okay, it is circular, meaning the base is circle. Okay, it's right circular cone, so it's like 90, the tips is 90 degrees to this base here. And then you want to put a cylinder here. Side. You want to find the largest cylinder you can put it. Maybe not this bottom. Maybe up to here. Okay. So you could imagine that this cylinder, right, the radius here should be restricted by this cone. Okay. And also the height. Okay, once your radius is get restricted, your height also get restricted. Okay, so there are certain relation here. But you want to maximize the volume. So let's see what's the volume you need to take care about. So the volume you need to take care about is at least this radius here, x, and also the height, this height here. Okay. But this height and this radius here really compare to the radius of your cone and the height of your cone. Okay, so well, what's the easiest way to do this? So the easiest way to do this maybe perhaps is to observe that there is a triangle outside this cylinder. So let's draw this triangle. So maybe this triangle has a height y, then your cylinder has height h minus y. Okay, so why are we interested in this triangle here? Because this is a triangle that we can compare to the triangle we could get from the cone actually. Okay, let's draw a triangle on this cone. Okay, how are they related? They are related by the similar triangle argument. Yeah, meaning the ratio is the same. Because these two triangles are congruent, or these two triangles are similar actually. Okay, so let's write down similar triangle. We can control these y and x by the height and the radius of the original form. Okay, so these two are 90 degrees. So we will have function as y equals to hash x over like that. But then we want to find the greatest volume, right? So let's write down the volume of the cylinder. Volume, let V cylinder to be equals to, what's the formula here? Pi x square times height. Okay. But we already write y in terms of x. So we really can express it in a single variable like this. Okay. So you can note that this is just polynomial. Okay. Polynomial is nice to differentiate. So the h and r is fixed here. It's not variable. Depends on what height or what radius you want. They are fixed. Okay. But x is not fixed. You want to compare. You want to compare like which let's see. Which x. Sorry, let me draw another x. Maybe another x is this. Okay. You want to compare which cylinder have the larger volume. Okay. So this is what this volume cylinder talking about. So this x is changing. H and R already fixed. You fix a con, and then x should be changing. So you got like small x to very big x. Maybe I draw another. So I want to see which one has the largest volume here. If you haven't learned derivative yet, what would you do is maybe you just put one x into it and then you compare. Okay, three of this, which one is largest? But you can notice that there are infinitely many values you can test on. Okay, so it's not a good idea to just do substitution and compare. But you have learned that you can use derivative to find the maximum point. Okay, so we should use the theory to check. Okay, so let's differentiate it. So now B prime cylinder is equals to, let's check the derivative correct or not. So 2 pi hx minus 3 pi h over r of x squared. This is pi hx of 2 minus 3x. Okay. So we have we? Oh no, we just factorize. Okay, we just factorize, though there are two portions of x here. So this means that if v prime x equals 0, this will implies that x equals 0 or x equals to 2/3 of radius. So is it possible that x equals 0 is the local maximum or minimum? Is it possible? If your x is 0, your radius is 0, your volume is 0. Okay, can't be maximum, right? Okay, but if you are 2/3, then it will be a maximum. Okay, so you can check with first or derivative test or second derivative test. Okay. So say that the maximum clearly occur when x is equal to 2/3. So if you sum it back, hence where is it? V cylinder is equals to vertex of that r square that's vertex of r and 2/3 of r cube. So all together you get 4/27 pi r square. Okay. So actually it's dependent on your con, a bit different from your con, right? Let's see. So let's check this value here. Do you remember what's the volume of con? I think it's 1/3 of pi r square h, right? So it's 4/9. 4/9 of the volume of your con actually. Econ. Okay. So you actually can get 4/9 of your con for the maximum volume of cylinder. Okay. So if you notice the way I draw the cylinder inside this con, right? The two-sided of the cylinder, not the two-sided, the whole circle of the cylinder at the top, right, should intersect with the con. Okay, this is what the inscription means. Okay, because you could imagine, right? I could just draw a small, well, I mean, I can just draw like a small rectangle, I mean, cylinder inside here, right? But it doesn't make sense, right? I mean, it makes sense, but this is not the question asking, right? I mean, I can like draw a random cylinder inside here and then ask you what's the volume of it, what's the maximum volume I can get. But the point here is this inscription here really fits what this inscription is trying to check. What kind of a cylinder you want to compare? Okay. Yeah. Anything I want to comment here? Yeah. So in the exam, right, please check these tests here. It's just that I don't want to repeat the calculation here. But don't ask me to check. If you ask me to check, you don't get marks. Okay, please check it yourself. Okay, any question? 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 If you notice the way I teach you guys, right, I will like focus more on methods. Okay, because I believe that if your method is correct, then your solution wouldn't be too far away. Okay, so but it is possible that your method is wrong, but you still get a correct answer. That's just lucky. But if your method is wrong, solution is wrong, then you are very wrong. That's all you are very wrong. So at least your method must be correct. Solution, we have now like a lot of computer to check already, right? You just tell computer how to compute, then computer will compute for you. Okay, so it's more importantly is the step you need to learn. Okay, because AI can compute better than you, but maybe they cannot work out the step yet. But they are getting better. Okay, continue. How about let's skip this? This is very similar question to just now one, which is about volume of some cylinder. Can okay, let's skip this. I'll provide solution. You can try and work it out. Let's do the next one, more interesting one. Let's try this one. So find the point on the parabola y squared equals to 2x closest to the point 1,4. Let's draw first. Let's draw this question first so that we know what are we expecting. So let's draw it. You know how to draw y squared equals to 2 squared. Right? Y squared equals to 2x. I think we all know how to draw y equals to x squared, right? So it's like parabola facing up. But now the square moved to y. Where the square moved to y? So how does it look like? Huh? On the other side. So facing the other way. Okay, so why is it facing the other way? One way to think about it is you can rewrite your function as y equals to y squared over x, right? Sorry, y squared over, sorry, what's this? Y squared over 2. Okay, maybe it's just by flipping your x and y axis, so because you know how to plot y against x, right? Now you plot x against y, so it's like this. So then you need to flip it around. Can I flip it here? Let me try. I think good knock cannot flip yet, only can rotate. So if you flip it, do you know what I mean by flipping? So make x and y swap. So it should turn the other way around like this. Okay. Or the other way to see this is not that x is equal to y squared over 2, right? Meaning what? X is always positive. So your x is just going to be positive. And then you know the basic shape already. So it's the parabola shape. Okay. Yeah. Few way you can think about it. You can think about geometry way, or you can think about the algebra way. Okay. So this is y squared equals to 2x like that. And then where is 1, 4 here? So let's check. Let's compare to our graph. So if I substitute 1 into my x, my y should be just square root 2 and minus 2. Minus square root 2. So 4 is a bit higher. So it's much higher. So 4 maybe like here. Okay, so this is the 0.14. Like that. Okay. So the question says what? Find the point on the parabola closest to this point. So what does it mean by closest? Obviously, you need to draw a line between this point and every point on this curve. And then you measure which one is the shortest one. Correct or not? Okay, so you draw a line from 1, 4 and then to every point on this curve. And then you compute. Okay, you compute which one is the shortest one. Okay. But obviously, you don't want to do this, right? Because these are too many calculations to do. Okay, so instead, we should write this distance as a function. Okay. Do you know how to compute distance between 2 points? Do you know? So maybe we should draw another picture. You know what's the distance? Let's say x1, y1, and x2, y2. You know how to compute this distance here? You know? Yeah? Yes? Yes? You can say? Try? Uh, okay, so actually you are using the Pythagoras theorem here, right? So really you turn this distance into some right angle triangle here. Okay, but note that the height of this triangle is like x2 minus x1. You take the larger one minus the smaller one. If you decide to take the smaller one minus the larger one, is it okay or not? Maybe you get negative, but one way to get around with this negative, you just put absolute values. Okay, or Euclid, no Euclid. The Pythagoras help you to put a square here. Okay, and then the width is similar, y squared minus y1 square, then you take the square root. Okay, so this is really, so Pythagoras theorem is really a basic block for us to measure the distance in our real world here. Okay, so for our case, so here, our d square is our one of the points fixed already, right? So it's 1 and 4. So we could get 1 minus x squared plus 4 minus y squared. Okay. So in this case here, we just get square root of 1 minus x squared minus 4y squared. Okay. But note that this xy is a random xy. But the y we care about is just those on the curve. Okay, so those on the curve that we only care about. So should we? Okay, there are a few ways to substitute. Maybe I give you some choice to do. So let's write down our assumption here first. By assumption, we only care about points on y squared equals to 2x. Okay, so what do you think? You want to substitute y squared or you want to substitute x? What do you think? So who say? You say you want x? You want x? Okay. So one way we could see is maybe we write our curve x equals to y squared over 2. Then we can substitute this x. Okay. Right. Should we expand this? Will it be easier to calculate if we expand this? Maybe let's expand this. Later we're gonna do derivative. 1 minus y squared. Right? Yep. And then plus y to the 4 over 4. And then plus 16 minus 8y plus y squared. Is it true? Yep. Let's simplify it. So 17 minus, sorry, no. So this one cancel, right? And then 8y minus 8y. Yeah, I think that's it. Correct? Please help check. Okay, so then now we want to find the maximum distance. Okay, so finding the maximum distance here will be equivalent to finding the local maximum or finding the absolute maximum. Then compare which one is the maximum out of everything. Okay, so let's do it. So in this case here, you will see that if I want to differentiate d with respect to y, right, I should use chain rule here. So let's call it dy lah, so that you not confuse the dy. Okay, let's write it as a function. Right, so how do we differentiate this? Okay, so we're going to differentiate everything inside first. So which we get negative 8 plus 4y cubed. Okay, and then we differentiate the square root. Like that. Okay, everyone happy with this chain rule? Or start again? Where? How come? Why it's stuck? Refresh. Okay, come out. Yeah, everyone happy with this chain rule or not? Maybe you want to write down the full step. What is your, or in this case is y, right? Maybe you should use another variable. Maybe use u. Right. Okay. Or maybe let me check. Yes, what's the chain rule you should use here? Maybe let's check. So you should use that d equals to square root w and then w equals to 17 minus 8y plus y4. Okay. Yes. Oh, 1 over 2 forgot, is it? There's over 2 here. Anything I miss? Anything I miss? Should be fine. Oh, this over 2 is good, right? I can simplify my my factor here. Huh? 1 over 4? Do we have 1 over 4? Oh, I think we have it, right? So let's check. 1 over 4. What do you mean by 1 over 4? Oh, I forget to cancel. Okay, thank you. Yeah, I forget to cancel. Okay, so yeah. So we cannot really divide out anymore, right? So let's keep it at the side. This one? Okay, good. Okay, good. All right. So we want to find maximum minimum. So we need to let this thing equal to 0. So consider the derivative d is 0. Wow, this thing have to be 0. This implies that y cubed has to be 8 over, oh wait, yeah. So this have to be 8. That's it. Okay. And then this implies that y have to be 2. Okay. Everyone okay, right? To make this 0, your numerator must be 0. Okay. Yeah, so what's your x? So should we use first derivative test? So if we consider from the first derivative test, okay, when y is less than 0, what do you get? Sorry, y less than 2, what do you get? When y is less than 2. Okay, to be safe, I just take y that's close enough to 2. We don't care very far points. Okay, we just care beside 2. If y is less than 2, what do you get? So y cubed would be something less than 8. So meaning your numerator could be negative. But the denominator, if it is something less than 2, then minus 8 times something less than 2 should be something less than 16 minus 16, right? So 17 plus 16 should be, sorry, 17 minus something less than 16 definitely greater than 1. And something close to 2 you take to the power 4 is still positive. And so what you get here is negative, right? So the prime over y is less than 0. Again, because y cubed will be y cubed minus 8 will be less than 0. And then another part is 17 minus 8y plus, or maybe just consider this 17 plus 8y should be greater than 0. Okay, so similarly, you could check when y is greater than 2. Okay, we just consider something close enough to 2. Okay, because it's a local maximum. You can see that d prime y is greater than 0. Why? Because you can compute. Y cubed minus h should be greater than 0 because you have 3 numbers that's greater than 2 and then you multiply them together. And then how about the next part? If it is close enough to 2, right? Okay, if it is close enough to 2, we can make sure that 17 minus 8y is greater than 0 as well. Okay. Close enough to 2. Okay, so very close enough to 16. So this is true. And we can also make sure that also make sure that 17 minus 8y is greater than 0. Okay, since we consider y sufficiently. Because you can actually anticipate that if I take too large y, right? If the y is too large, right? Then this thing will go to negative. Could be, can or not. Maybe you need to check. Is there a point that it goes to negative? Or even go to 0, then you are, I think you won't go to 0. But this sum here, you need to make sure it's not negative because you cannot take square root of negative number. So from here, we can see that what can we see here? So are we looking for maximum or minimum in this case? Find the point that's closest. Closest, right? So meaning the shortest one. So this is the minimum distance here. So is this a good local minimum? So let's check. So on the left-hand side, you are decreasing. On the right-hand side, you are increasing. So this is a local minimum. And then I think there's no other point you can compare with. So hence, the first derivative test. This is the local minimum, and then this is the only minimum. Wait, so you are 2 here, and then your x should be written in terms of 2. Your x is y squared over, or which is 2 squared over 2, which is 2, 2. Is the closest point on the curve to 1. Okay. So we choose to substitute x equals to y squared over 2, right? But there's another way to do it. You can substitute y as well. Okay, you can substitute y as well. So meaning you need to decide which y you want to substitute. But if you look at this function, right, it is y squared equals to 2x. So there are two possible y's, right? So actually you have y equals to square root 2x, y equals to square root minus square root 2x. Okay. Which y you want to substitute? So what are these two y talking about? So one y is always positive, right? One y is always negative. Actually, this two y, right, describe the two parts of your graph here. Okay. So if you want to find the shortest one, would you go for the negative one? Negative one is definitely further than this y equals to square root 2x, right? So you could try substitute y equals to square root 2x and then do the same similar calculation. Actually, I go for the long way. And the calculation get a bit scary, but still doable. Again, I still get the same answer as well. You see, the chain rule I did on this square root over square root function. But you still can get the answer actually. It's the same answer. Okay. A bit scary, but doable. And actually the textbook uses the y square one. Yeah. So the textbook use the easier way. So he consider the whole curve if you want to think about it. But I just consider half of it. Okay. I just consider half of it. The textbook consider everything, and then I consider half of it. But still doable at least. Still okay lah. Not too difficult, but it's very tedious. Okay, makes sense. Yeah, you should try. You can try out. Very fun. You can try out. Okay. And then one last one is similar question inscribing. So maybe I will just skip it. So what's this picture? Maybe talk about the picture first, and then we can skip the step. So let's form this picture, and then we can take a break. Okay, so find the area of the largest rectangle that can be inscribed in a semicircle. Okay, so again, it's an inscribing question here. So, well, you need to get your shape out. So first is the semicircle, and then second is the rectangle. So we need to draw the rectangle. Okay, so what's the relation you can write out here? Okay, what's the relation you can write out here? So what's the question? Area of the largest rectangle. So meaning at least you need to label your rectangle first. Okay. But then how do you relate to your semicircle? Obviously your semicircle must have a radius, right? Okay, but how are they related? Any idea? Any idea? How should they related? Is it better than I call this y and then call this x? Because this is horizontal. Any idea? Sorry? Sorry? Sign? Use sign? How to use sign? So maybe one hint, maybe you can try your sign method. If you success, let me know. Maybe you can try this 2 point here. What does this 2 point have to satisfy? These 2 points lies on the semicircle. Do you know a formula for semicircle or not? You know the circle, but you know the circle is very, then you will be very close to the semicircle already, right? Because the circle is y squared plus x squared equals to r squared, right? Then the semicircle is just take 1/2 of it. Right. So if I draw like this, that means I want to take the upper one. No? If you draw the other one, you take the lower one. Okay, so we just take y equals to square root r squared minus x squared. But this x is still a bit different from the x above, right? This x inside your semicircle is a bit different from this x, right? Okay, so how do we really find this x? If you like, maybe you can relabel this as minus x and x. Then your length will become 2x, like that. Okay, makes sense? I mean, this really depends on how your semicircle and rectangle inside your coordinate. The way we choose to put this is we put it as the origin. Okay, so it's symmetric. So it's symmetric. Because semicircle is symmetric, so we can do this. Okay, because semicircle is symmetric. Okay, then the area in this case will become just 2x times y, which is 2x times square root r squared. So if you're given this, you can compute already. Go find your first derivative, find your stationary point, boundary point, or whatever point, and then compare which one is the largest. Okay, any question? I think the hardest thing is to build this relation. Okay, building this relation is one of the hardest thing you need to do in this type of course. And relation between these variables is important. I think especially important in your course. And you need to determine what variable, what data is related. Okay, question? Any question? Know how to continue? Okay, so I'll try and do it. Yeah, this derivative is a bit tedious also because there's a square root inside there. Okay, before we finish, 4.8, we won't be covering this. It's not in your test as well. If you want to learn it, it's fine. Did you learn this in your pre-university before? Before you come to university, Newton's method to find roots. Got learned before? Okay. Yeah. We won't cover this in our test, but you can learn yourself if you want it. But this is just some application of our derivative. Okay, so basically Newton method is you couldn't find the bound. I mean, you cannot find the root. You cannot find the root of your function like quadratic formula, something like that. No formula to find roots, but you can guess your root. So you guess your root one by one, iteratively, until you reach very close to the roots. This R is where you want to reach. Yeah. But this is not in the test. It's not testable. But if you want to learn it for yourself, it's fine. Okay, so let's break again until 11, 12. We will come back with antiderivative. So quiz will be up to 4.7. Okay, 4.9 is not included. So after quiz, we'll come back with this section. Okay, let's break until 11, 1, 2.
Tu rispondere anche queste sensorie, c'è scuola. Pokoknya matrilisnya sampai sini kamu harus buat taruh kecil. Kamu tinggal sama gitu. Baca semua. Tadi kamu buat semuanya cara itu.
就是这个问题是这样子的，就是它这个就你今天讲的题，它前面通着关系，它可以得出这个 H 等于 R。那如果说就是我在用 DV 处理机器人里面，我不把它的那个就是 R 给转换成 H，可以吗？
因为它两个都是变量，所以你如果有两个变量呢，
一定要组成一个。
因为它只给你一个变量的那个资料吧，
对，
除非它给你 DHDT 跟 DRDT，因为也不行，因为如果有两个变量的话，它的 derivative 是不同的。你应该有上过 calculus 2是吗？
对，有的。
对，是不同的。
那就是我知道这个是个变量，那我现在对哦，是 DV。那如果说这个地方是 DH 的话，那其他的我都可以不用管。
我想看这样子。DH 的话，但是你 DH 的话，你还是会有 R 在里面，对不对？
就是
它这两个变量一定是同时在跑着，你明白吗？它两个一起变，
那
所以你只能够把它另外一个把它联系到另外一个的，你才可以同时看两变，你懂什么意思？
我懂。
耶，
那如果说这个 R 是个变量，但是它跟 H 不带这种关系，就比如说
就不能这样解啊，这是两个方向的问题啊。
那就是我不知道这个 R 怎么跟 H 变的话，我就不可以直接这样子得出来的。
因为他们会不同的变法，可能就是两边的变化是没有关系。你要分开说。
但是我想到之前，比如说求导，然后有一些它前面是 x 平方，后面是 y 平方，然后呢，它对 x 求导平方，然后它相当于把那个 y 给当常数啊，那样子，就是他说就是不变。
呀，
对啊，那我在这里为什么不可以这样？因为我那个把 y 那个不变的话，
那个不变是说，你对这一个 y 的方向看那个 xr 怎么变吧。那个的意思是那个，你知道什么意思吗？就是来对这一个 h 的方向，你能够想象吗？这题你想象不到，你不可能不变 h， 但是把 r 变掉，这样的话你的一开始的东西会变。
对，
对，就是对，你刚才讲的东西就是就是怎么说呢？你是在一个高度，你看这个 r 怎么变化但是这个情况不可能。你如果
他们是一起变，
因为如果它一不变，它的 radio 也不可能变，
那
除非你的一开始的东西在变。这样不可能嘛？因为我们现在的条件是我已经 fix 好这个 tank 了。
对，
你那个是对，那个就是刚才我们说的，就是我说的就是它有两个方向在变化，但是我们是 fix 一个方向，然后再看另外一个方向这样变。
好的，反正就是它两个都是一起变的话，那就把它转成一个关系。
对，因为在这个课里面你只能够一起变，因为我们只学 differentiate 一个。
假如都是考试考的，它也都是一起。
肯定一起变，不然的话你做不出。
好，
不然我们就要用考格式。
好的。
Can we use methods of this?
Inequality.
Yeah, inequality.
So this is not equal. This is
not equal.
Then how do you make it?
And just in that way.
So wait, you this one get this, then this is what?
Then this is this.
This is this?
This is A. This is
okay.
B, and
But this one is less than equal, not equal, right?
What do you mean?
If it's equal,
then
A plus B plus C, and we will find the maximum.
Wait, let me think. Oh, you mean when this is equal, then this is equal. Oh, I mean, wait, let me think. Or maybe the question is, why is this the maximum? Why not something? You understand?
Of course.
What do you mean, of course? You just found the bound, right? We just know that this is bounded below by this. How do you know this is the maximum? You understand what I said? How do you know this is the largest? Like what I said last time, right? Maybe this is 2, right? 4 also can bound. Why not 4 in the...
Oh, I know what you mean. I know.
Yeah, why you cannot attain the 4? I don't know. Yeah. Yeah. So you need to address that question now, why you cannot attain other maximum. I mean, at other bound as the maximum. Yeah.
That's true.
Correct.
And another
Yeah.
question is also we can use that way. Just this.
Yeah. I mean, same.
Yeah,
I
the
think same argument. No? Yeah. Why? Yeah. Why is this the only maximum you can attain here?
So in the examination, we can use this.
Obviously, this is just some inequality.
Oh,
Yeah. Free meaning. What? Maybe I start first. You ask me again after. Oh, yeah. It's going to start soon. Okay. Let's continue for the last hour here about antiderivative. So this section here is preparing for integration. Okay, so please take note. Maybe you might think that this section is very simple, but this is preparing for integration. Okay, for the Chinese student, you haven't touched integration before, is it? No, but okay, so please listen carefully. Yeah. So here is the preparing for it. So let's see what is antiderivative. So derivative, anti means opposite. Okay, opposite of derivative. So what do we mean by opposite of derivative? So we will call f an antiderivative of f if the derivative, okay, of this capital Fx here is the little fx. Okay. So we will say that f is an antiderivative of f if x prime x equals to fx. Okay, does it make sense? So if you have a function differentiate to another function, then you are the antiderivative of that function. Okay, so an antiderivative is a antiderivative of f. How should I put it? And the derivative of the antiderivative of f is f. Okay, let me write down. The derivative of an antiderivative of f is f. Okay, can memorize this slogan here. The derivative of an antiderivative of f is f. Understand? The derivative of an antiderivative of f is f. Okay, so where's the nouns here? Derivative, antiderivative of f. Can you memorize this? The derivative of an antiderivative of f is f. Okay. So derivative of an antiderivative of f is f. Okay. Okay, so let's look at some examples here. So which one is the example? The easier one is let's start with the third one. And let's start with the third one. And let's start with the third one. So we say that Sn plus 1, s to the n plus 1 over n plus 1 is the antiderivative of xn. Why? Because if you differentiate it, Sn plus 1 over n plus 1 is s to the n. Correct or not? because what do you get? You get n plus 1 times x to the n over n plus 1. Okay? So the derivative or the antiderivative of f is f. Okay, so whenever you talk about antiderivative, you need to always mention whose antiderivative. So similarly, for all the rest, let's say look at this. What's the antiderivative of sine x? Okay, it's negative cos x. Why? Because if you differentiate it, negative cos x, what do you get? Negative of negative sine x, which is sine x. Okay, make sense? Okay, so why is it opposite? Because you really think of an opposite operation of derivative. Correct or not? You see, if you look at this example here, instead of multiplying by the powers, you are dividing by the powers here. When you go from xn to xn plus 1 over n plus 1, you are like add 1 to the power and then divide by the new power. Because if it is derivative, what do? You bring down the power and then you minus 1. So it's like opposite of derivative. Make sense or not? Does it make sense? Okay, it's opposite, really opposite. That's why we call antiderivative. Okay. Yeah, so for the rest, you can see that this table is the opposite of derivative table you had last time. Shall I bring it up for you? Maybe I bring one of them up. Let's go to the three goal topics. Those are derivative. Maybe go for the three goal one. So three goal Lisa. Okay, maybe this one. So if you look at this one, this one is not shown, right? Let's look for the tangent one. I think this one is enough. Let's bring this first. Okay, so you can see that this is like an opposite table that you have for derivative. Okay, can I find the sine inverse one? Let me find the sine inverse one. Yeah, this one, good. Copy, paste here. Okay, so you can see that it's the opposite table you had for a derivative. So you can see that everything inside the derivative is called the antiderivative of your derivative. So the derivative of the antiderivative of small f. So that's mean we call the thing inside this derivative of antiderivative. Okay, so far so good. Anyone notice that this antiderivative might not be unique? Might not be unique. Because you should remember that when you differentiate constant, what do you get? It's 0, right? So you can actually add any constant to your antiderivative. Then that constant part will disappear. Okay, so later we will see how important is this constant part. Okay, when it's during the calculation. All right, so let's look at some examples. Okay, so let's find the antiderivative of this f here, x squared. So meaning you want to find capital Fx, okay, such that the derivative of this antiderivative is equal to little fx. So our little fx is x squared. Okay, so what do you differentiate? Okay, such that you get x squared here. Okay, so what's the power you need to bring down and then -1, and then you get x squared. So you need to think the opposite way, right or not? Okay, so the opposite way is I'm gonna increase my power first. Only then I can decrease back to x squared. So I increase first, and then because later on when we differentiate, we need to bring down the power, so we need to cancel it out because there's no constant. I mean, yeah, multiply to x squared, so we need to divide by +1. Okay. But then, like what we discussed just now, you can actually add a bunch of constant to this. Okay, so actually, you take fx to be x to the cube over 3 plus c for any c in your number. Okay, so there's a list here. There's a bunch of antiderivative of this x squared. So do you know what's the geometric meaning of this? What's the geometric meaning of this? All these antiderivative, you look at the first derivative, meaning what? You look at how the tangent line changes. Is it the same way that changes or not? The shape is the same. So they should change similar way. Does it make sense? So if you draw tangent line on all these curves, right, they should change the same way. Okay, no matter what your y value is, they should change the same way. So that's why their derivative is the same. Okay or not? Okay, the way that the tangent line change is the same. Okay, so maybe I make a remark here. Not that for all antiderivative of f, their tangent line changes the same way. Okay, so that's why their derivative is the same. Okay. So derivative is the gradient of the tangent line. Obviously, tangent line is different, right? Because one is above, one is below, but their gradient is the same. The way they change is the same. Is the gradient. Make sense? Okay, so there's one proposition here is if fx, capital Fx is an antiderivative of a small fx, then so is all the capital Fx plus c, any constant. Because you differentiate c is 0. Question? Any question? Know the meaning? Why different antiderivative can get the same derivative? Because the way of the tangent line changing is the same. Okay, how about the next one? Let you try. Maybe let you think about 30 seconds. What's the antiderivative? X power 4. X power 4? Sorry, plus c. Okay. So let's try. So Felicia said try x to the power 4 plus c. So how to verify this? You just differentiate. Okay, so let's differentiate. Sanity check. So let's check it. So we differentiate x to the 4 plus c. Do we get 4x cubed or not? So we take 4 go down, x, 4 minus 1 plus c, you get 0 after differentiating. So you really get 4 to the x cubed. Good. Okay. Yeah. How about the harder one? This one. Okay, this one give you longer time. 1 minute and a half seconds. 19 seconds. I want to try. Okay, let's try. So take capital Fx to be minus 4. Then cos x. Okay, cool. Mm-hmm. Mm-hmm. Minus half. And then what do you get? Minus half and then x. Root x. At the bottom or at the top? 1 over 2 root x. Up. So root x over 2. Okay. Plus c. Okay. Any other solution or not? Check. Oh, we need to check. Let's do sanity check here. So let's check it. Let's do differentiate this antiderivative here. So what do you get? So 4 sine x plus 2x to the 4 and then minus half of square root x and then 0. Okay, does this match up or not? Okay, maybe not very clear yet. So let's simplify our g prime x. So let's simplify it. 4 sine x plus 2x to the 4 minus 1 over square root x. Oh, there's a half coming up. Okay, so can we modify it? How to modify? How to modify? There's an extra half. How to modify? Huh? Hey, do I differentiate wrongly? I think I differentiate wrong, right? This is 1 over 4, right? Extra 4 factor here. Is it? I differentiate this term off. Differentiate minus square root x over 2, correct or not? The half have to bring down. Sorry? What can I do? Can I modify my antiderivative? Which one? Which part? Last one? Above? So we're going to modify this term, is it? So we need to modify this term, right? So become minus 2 root x instead of over 2. Is it? Wait. So now you agree that solution is wrong? Do you agree? Because this checking doesn't match up with G prime. Match or not? This is 1 over 4 square root x. This one is 1 over square root x. Salah, betul atau salah? Salah kan? Wrong, right? Because it doesn't match up, right? Or your differentiation is different here. You differentiate here correctly or not? You wait in check. Okay. So everyone see right, this one right. So we need to do modification. So after say we move this over 2 become 2. Okay, so let's see if it works or not. Okay, so what if we make this 2 here? Then here will become minus 2 times 1 over 2 of 1 over square root x, which is 4 sine x plus 2x plus 4 minus 1 over square root x. Okay, good. Okay, so when you propose the antiderivative, right, make sure you differentiate to the function that you want to check. Okay, so now let's try 4.63. This you can see that there's an extra condition here. So maybe let me move this. Okay, so if you look at this question here, there's an extra condition here, which we could call it a boundary condition. Okay, so there's a condition here. Then this condition will make you decide what C you use. Okay, I'll let you try this question. Give you 2 minutes. Let you try what's the antiderivative of this derivative here. Yeah, I'll let you try this question. Okay, anyone try? Have you get any answer? Anyone? I think EX should be EX, right? How about the other one? What's the antiderivative of 1 over 1 plus x squared? Sorry? Tangent inverse x? Good. Okay, so you can refer back to your tables. The derivative of tangent inverse x is 1 over 1 plus x squared. Have you found your constant? Found your constant? Not yet? Okay, try. There's only one constant will make this f0 equals to minus 2 work. Anyone got the constant yet? If you got it, maybe you can shout it out. Got it? Minus 3. Okay, good. I think you're right. So let's check. So our antiderivative is EX plus 20 tangent inverse X plus C. Okay, so you should do the checking. So let's do the sanity check that f prime x is indeed little f prime x. But then there's some extra condition you need to check here. So let's check the condition at x equals 0. So minus 2 is equal to this f0 here. So meaning this capital F0, which is e to the 0 plus 20 tangent inverse 0 plus c. Then you get 1 plus c, which is implied that c is minus 3. So you just take, so we will take, so we choose little fx here to be e to the x plus 20 tangent inverse x minus 3. Okay, does it make sense? Okay, so meaning if once you fix a point on your antiderivative, right, you are actually picking one of the antiderivative. Okay, so if you look at the picture here, right? Let's say you want this antiderivative to contain, let's say, some points on the blue line here. Okay, maybe a bit hard to see. Maybe use this color. Very similar color, huh? Use the red one. Okay, maybe you want to say that your antiderivative contains this red point here. Then your antiderivative could not be other function other than the blue line here. Okay, you are taking a constant out of it. Okay, make sense? Any question? Okay, if we didn't specify what this antiderivative is, then these are the possible antiderivatives. Okay, once we specify, we take a point, and then this will determine which one you pick. Okay, so 4.64 here is similar. Okay, just that they ask you to do twice. You start with the second derivative. Okay, you do it twice. Then we will skip this. You just do it twice. How about do this one? Okay, do this particle move. So particle move in a straight line. So maybe you can draw it. Particle move in a straight line. Has an acceleration. Wow, acceleration. Acceleration means what? Second derivative of your displacement. Right. So this is the second derivative of your displacement, which is equals to the first derivative of your velocity. Okay, we have met this a lot. So, and the initial velocity is v0 equals to -6. So it's in the different direction. And its initial displacement is S0 equals to 9 cm. So you start at the 9 cm here, maybe 0 cm here. Okay. So what should you do? You also find what's the question? You want to find the position function xt. So meaning again, you want to find antiderivative twice. Any question about this? Any question? Should we do this together? Or you are okay? Should we do this together? This is a question. So I expect an answer. Do you want to do this together or you are okay? Huh? Felicia? You want to do it yourself or we do it together? Up to me. Up to you. I let you choose. I want you to learn to make choice because maybe when I was young, right? A lot of choices are already made by people. So I want you to learn to make choice. At least inside my class, you are free to make choice. Or you are free to make mistakes. So although if you make mistake in quizzes, maybe you lose mark. But I hope you learn from these mistakes. So want to do it now together or you can do it together? Okay. So let you do it. Okay, let's do it together. I think this one is quite easy, so should be pretty fast. So we'll consider taking VT to be so let's see. VT should be so you should increase your power, right? Instead of decreasing, so +1, and then instead of multiplying by this power, you divide by this power. Okay, so this is the way to do it. And then for what thing differentiate to 4, you need to put in a variable into it. But this is antiderivative, right? It could be differ up to a constant. So 6/2t squared is 4t plus c, which is 3t squared plus 4t plus c. Okay, so A very earnest advice is please do the sanity check. So meaning you differentiate it again, see whether you get your derivative or not. Okay, so you can quickly check actually in this case. So if you differentiate Vt here, 3t squared becomes 6 times t, 4t becomes 4, and then c becomes 0. So you get the acceleration. Okay, so sanity check here, meaning you need to check that v prime t here is really equals to at. Okay, but similar to the question we did before, right? We already determined a point inside this VT graph here. So meaning we are picking a specific C. Okay, so how to pick? You need to substitute your points here. Okay, you need to substitute your points here. So by assumption, you get, what do you get? Minus 6 equals to V0, which is just evaluate to C. Very nice. Okay, because 0 times 3, 0 times 4, you get 0. So C is minus 6. Hence, we choose Vt to be 3t squared plus 4t minus 6. Okay, then you continue. Okay, then you continue. Okay, so to find x, how to find x? So to find x, t, okay, it is the antiderivative of x prime t, okay, which is equals to Vt. Okay, so you need to do the same game. So consider St to be, let's do it quick, 3 cube plus 2t squared plus, sorry, minus 6t plus d, let's say call it another variable here. Okay, so we need to do a sanity check here. For this sanity check, right, you can check in your exam. I think last time there's only few of you check the inverse function. Okay, not every one of you checking, but I hope that you check yourself. If not, you check in the paper. Okay, it will be safe. So how to check here? You should check that x prime t here is really equals to Vt. Okay, so let's quickly check. So t cube here, okay, you differentiate, you get 3t squared, 2t squared here, differentiate, you get 4t, and then minus 6t here, differentiate, get minus 6, and then constant differentiate against. Okay, so you get that your Vt. But again, this graph here is chosen a point which is 0, 9, S0 equal to 9. So you need to pick your D now. So by assumption again, 9 is equals to S0. So if you substitute 0 into your ST, what do you get? You just get D. So your D is 9. So hence, we pick ST equals to 3 cube plus 2t squared minus 6t plus 9. So this is your final answer. Okay, so your particle move using this polynomial. So when you put t equals 0, your particle really start at the 9, and then increase like this polynomial. Polynomial of degree 3, which is a cubic. Okay, any question so far? So now we are kind of working backward. Okay, backward of derivative. For the rest of the half of this course will be integration, and then at the very end, okay, we will combine derivative and integration in the differential equation. Okay, combine both. Any questions so far? Questions so far? Any questions so far? Oh, is it good time to stop here? Stop here, good. Okay. So go back, please do revision. Next week. After your quiz, we will start with integration. Yeah, after your quiz, we'll start with integration. Yeah. Okay, take your time to do revision. Arrange your time wisely. And then have enough rest. See you next Wednesday. Yes. We will announce after quiz, but should be until here. Should be until here, but we will announce it after quiz. Okay. 下周一，那3点，
就线上
线上对。
OK。
呀，摩德那边有 announcement。